next part of the Open 5G forum for today, we show you how basically we use one of the platforms that are publicly available to the wireless community in the US to run open 5G experiments, right? So we organize the session in this way. First, we give an introduction on basically what Colosseum is and on what in general you can do with it. And then we'll focus specifically on how it can be used for emulation of cellular networks. So today we'll discuss about how to use srsRAN in Colosseum and the experiments that we did with ORAN and srsRAN in Colosseum. And tomorrow, instead, we'll have, after the OAI talk, we have an introduction on how you can use OAI in Colosseum. So this is a platform that is available and that can be used to do research on the design of 5G systems. So let me share my screen. And again, I'm going to invite you to use the chat and Slack for any question. We keep monitoring it, and we'll be able to answer any questions. All right. So let me start with a brief introduction on Colosseum, what Colosseum is, how you can use it, and so on. So Colosseum is a US national resource for wireless system research. Colosseum has been developed by DARPA and Johns Hopkins APL to provide a platform for the DARPA Spectrum Collaboration Challenge. And it's a massive, it was a massive investment that built an emulator which has one of the largest scales available. After the end of the Spectrum Collaboration Challenge, Colosseum transitioned to Northeastern University. And thanks to the support of an NSF grant. And it has joined the overall Platform for Advanced Wireless Research ecosystem to basically create a connected ecosystem of wireless testing platform. Right now, Colosseum is, we operate Colosseum and is publicly available and supports multiple remote users on a shared access. And you can use Colosseum to do research on a number of different wireless related topics from 5G to spectrum sharing to AI on wireless and the Internet of Things. So just to put an image on what Colosseum actually is this is a picture of part of the infrastructure. And Colosseum is a large-scale RF system, emulator for RF system with hardware in the loop, in the sense that it has actual radios. So there's 21 racks of radios and high-performance servers with CPUs and GPUs. There's so the radios are USRP X310s. So in Paul's presentation, at a certain point, he mentioned that they were testing their code on similar SDR-based platform. So the Colosseum features these 256 radios, 128 that can be used by the users, and 128 that are part of the emulation platform. And overall, you can emulate 65,000 channels, each with 80 to 100 megahertz of RF bandwidth. So, and of course, with a full mesh networking capability. In addition to this, Colosseum is a massive computing facility in the sense that it has CPUs, it has GPUs, it has FPGAs. And we're also working on integrating an additional set of state-of-the-art GPUs that can be used by the users of Colosseum. There's storage, so more than 900 terabytes. There's multiple FPGAs, and there's this infrastructure is used to create diverse scenarios that, for example, as we'll discuss in a moment, can be used to allow AI and ML model to better generalize. So in general, Colosseum, as we say here, is more than a supercomputer, right? It's not only a data center, it's a data center with hardware in the loop. And it's not only a simulation environment. Thanks to the fact that it has hardware in the loop, it allows to do real-time emulation with the transmission of real radio signals, right? So for example, you can have an srsRAN base station running and receiving signals from actual srsRAN UEs rather than having all of this implemented through a simulation. And srsRAN, just to make an example, you can actually instantiate different software-defined radio protocol stacks in different emulations, in different experiments, or also in the same experiment, for example, to study spectrum sharing challenges. So it combines in a single instrument the flexibility of a virtualized platform, the fidelity of hardware-based emulation, and the scale of a network simulator, because with the 128 software-defined radio that are available to the users, it really allows you to create networks at scale. And it has been developed with a multi-million-dollar investment from different entities, including DARPA and the NSF and Northeastern. So in practical terms, this is the architecture of Colosseum from the infrastructure side. And in a minute, I'll also show you how this can be viewed from the experimenter side, from the user side. So the core of Colosseum is this MCAM, which is a massive channel emulator that accepts the signals from the radios as input and as a fully connected mesh that allows to account for propagation between each pair of radio, interference, multi-tap fading, and so on. Then the radios in Colosseum are part of the so-called srsRANs. And we have 128 of them. And each srsRAN combines a server, which runs a dedicated container, and a radio, an USRP X310. And these srsRANs are connected together and are connected to a traffic generator, which basically generates traffic according to predefined patterns and can drive the network emulation. Besides this, there's a side that the users generally do not see. There's a whole management infrastructure that with dedicated networks that is used to run the whole system. So just to give you a couple of additional details on the channel emulation part. So the emulator is based on a fully connected mesh of FPGAs that take the input from the USRP X310 of MCAM. Basically, for each actual radio transmission at the user side, so on the left part of the slide, you have the up conversion to RF frequency on the user X310. And then the MCAM X310 down converts it again to baseband so that the signal can be processed inside the channel emulator. The channel emulator is driven by a so-called scenario server, which streams to the emulator the RF tabs that represent the scenario. So we can model up to 4 multipath components in a 512 tab channel model. So there's 512 tabs, and of these, 4 are non-zeros. This allows us to, and we'll see this in a moment, it allows us to create virtual scenarios that can represent different wireless realities, right? And test the same protocol stack in different conditions. So as I mentioned, a standard radio node, or srsRAN, is a combination of a physical server, which is a Dell compute node, on which the Colosseum infrastructure deploys a container with the software for the specific software for the emulation. And the server is then connected to a software-defined radio that is dedicated to the server. From the user's perspective, this is what you see if you want to do an experiment with Colosseum. You have an experiment website that you can use to reserve the resources of Colosseum. And then you can SSH into the srsRANs that you have allocated to start the experiments. And you actually have 2 ways of doing this. One is through batch experiments, and the other is through basically interactive experiments. With the batch, in the batch you have the experiments that run autonomously. In the interactive experiments, you actually get to control and instruct whatever needs to be done during the experiment. So I see there's a question on the chat from Paul, which is a very interesting question. So what kind of end-to-end latency is added by MCAM? So, and there are 2 considerations here. One is the latency of the scenario, and the other is the processing latency. So the latency that is supported by scenario corresponds basically to how long it takes for the signal to be convoluted to the 512 taps, which corresponds to a latency that geographically corresponds to an area of 1 kilometer by 1 kilometer. There's an additional latency due to the basically the traveling of the signal in and out of the FPGAs, and that at most with the longest possible path takes around 15 microseconds. And I hope I answered your question. There's another question, so I'm gonna answer it now, but I'll finish the presentation. Yeah, it's another very good question. So why do we need to go into the RF domain and then go back down to the baseband? And the answer is that whenever you use an actual radio, you introduce some impairments that can affect the waveform. And having that in the this piece of hardware in the loop adds an additional layer of fidelity to the emulation. All right, so who can use Colosseum? Colosseum is free of charge for NSF supported researchers. There's special conditions for the researchers, and for industry researchers and researchers from that are not funded by the NSF, please email us and we can coordinate on a scheme to basically get access. So if you are interested in using Colosseum, the takeaway from this is that you should email us, and we'll work together on how to make this work. And as a platform, we make it available, and it's a goal for us to allow as many users as possible to access the system. So how this introduction brings me to the core point, right? Which is how can Colosseum be used for open, programmable, and virtualized systems, right? And because in terms of waveforms, Colosseum support any waveform that an SDR support, right? As long as it's inside the 80 megahertz bandwidth that is supported by the channels. But in this sense, we can use Colosseum to study, for example, sub-6 gigahertz cellular networks. And we do this, to do this, we provide a combination of scenarios and software profiles. So scenarios are, we design specific scenarios for cellular deployments with star topologies, with some base station and some users which move randomly in the scenario. And there are customizable source traffic profiles that can match, for example, different cellular applications. And then we provide software profiles. So we have containers for srsRAN for an extension that Leonardo here at Northeastern has developed. And we have and more of this in a few minutes. And we have containers for open air interface. And we'll comment more of this tomorrow. So just to conclude this briefly in terms of cellular and 5G capabilities, Colosseum can supports a number of scenarios with multiple base stations, multiple interface base stations and users. The users can have different mobility patterns, for example, like a pedestrian user mobility. And we basically created a few virtual scenarios that mimic real-world scenarios, including the actual Colosseum location in Rome, the Boston Public Gardens, and the powder testbed in Salt Lake City. Besides RF scenarios, we can also create virtual traffic scenarios. So using this TGen, which is based on a traffic generator called NGen. Or we can use, for example, iPerf or NetPerf of different kind of traffic generators to bypass TGen. So this actually brings me to the end of this slide deck, and I hope you got an idea of the capabilities that you can have with Colosseum. And I'll hand over the floor to Leonardo, who will show how, for example, you can instantiate an experiment using srsRT profiles in Colosseum.
Thank you, Michele. Hi, everyone. I am Leonardo Bonatti. I'm a PhD candidate at Northeastern University, and I will give you a quick overview on how you can use srsLT on Colosseum. So, as Michele said, Colosseum handles reservations from multiple users through containers. So you can log into Colosseum website, and I will share you my screen right now. Yeah, I think you can see my screen. And basically you can log into the Colosseum website that I have open here, and you can basically submit a new reservation to use some of the Colosseum resources, so the servers and the radios. So for instance, if I want to submit a new reservation on Colosseum, I just log into the Colosseum website, that is experiments.colosseum.net, and I go to the reservation tab, and I click the plus button to submit a new reservation. Here I can insert all my parameters, like the name of the reservation, like test reservation, the start date, the start time, and the minutes for my reservation. Apart from these basics parameters, I can select the number of sRANs, so Colosseum resources such as servers and radios, I want to allocate, like, let's do 4 nodes. So this counts as 4 sets of compute server and connected radio. And then I can select my LXC image that I want my radio to run. So in this case, I have a prepared image for this demonstration. You can both select the image for all your nodes, or you can also change an individual image for one of your nodes. Like, you can select one of the other images, like the base images that we have, and we have quite a few images to start using Colosseum. After this, you can just request a reservation, and your reservation will take a few minutes to start and to actually be usable. So for this demonstration, I made the reservation like half an hour ago, and I'm going to use this to speed up things. So I can go in my reservation and I see my radio nodes. I have 4 radio nodes reserved for this. And I can access the radio nodes through this host name that Colosseum knows how to resolve. And in this case, Gladiators is just the team name for this demonstration. So this said, I have a terminal session open on these 4 nodes with a channel emulator already started. And I'm going to start on my first node, my core network and base station. And while on the other 3 nodes that I have, I'm going to start the users, and I will exchange some traffic between the base station and the users. So first, let's start the core network in the first tab. And then I'm going to start the base station. This will take a few moments to connect to the radio and actually start. And we can see now that the base station has started successfully. So I'm going to go to another terminal of one of my other Colosseum resources and start the user application. This user should start similarly to the base station and should connect to the base station. Yeah, so we can see now here that the user successfully connected to the base station and got an IP allocated to it. Now on the base station side, to exchange some traffic, I'm gonna I'm gonna start an Hyper-3 server to which my user will connect and start generating data. So here we can see that the user manages to successfully connect to the base station and exchange traffic. And similarly, I will start other 2 users on Colosseum. As before, the application runs on the server that connects to the radio, and then actually uses the radio as radio interface to connect to the base station. So we can see that both users have been connected and they received an IP. So now I can start an Hyper application on the users as well. This will contact the base station and start exchanging traffic. So you can see that the second user started exchanging traffic with the base station. And my third user is starting as well to exchange traffic to my cellular base station. And to go back to the base station view, we can see that all the users are connected and they're generating some traffic for my base station. With this container that we made publicly available to each of Colosseum users, you can just really start the container, and you don't need to install any additional application, because installation setup and so on of SRS has been taken care by us already. So you can just start your the Colosseum resources with this specific container that contains a SRS already packaged and made available for users, and you can just start base station and users applications in a matter of minutes. I think, yeah, this is it for the quick demonstration of how to use srsLT or srsRAN on Colosseum. And I see that there are some questions in the chat here. Let me just see this question. So I think there was a question from Andrea about UHD. I've seen that around. Okay. So our experience on different UHD version and stability. So on Colosseum, we're using, I believe, the LTS versions of UHD, and those are quite stable. And by default, Colosseum, for legacy reasons, basically preloads on the radios 3.9 UHD FPGA image, and this is for legacy reason and retrocompatibility with what Colosseum used to run during the DARPA Spectrum Collaboration Challenge. But users can program the FPGA with any image they want, so other images from UHD or in general other FPGA images they might want to design. So I would say we tested LTS versions of UHD, and they are quite stable. Then about the waveforms of Colosseum. So Colosseum uses USRP X310 radios, and these radios work at sub 6 gigahertz frequency. So you can use the spectrum up until 6 gigahertz of frequency. And for the bandwidth, basically, there is a 80 megahertz limitation bandwidth that is due to the MCAM channel emulator processing. So as long as your application fits in this bandwidth, you can use any frequency below 6 gigahertz. What is the latest 3GPP release supported by Colosseum? So Colosseum can, in general, run any software-defined radio application. So it's not limited to cellular application, but you can also run other stacks, so Wi-Fi, Bluetooth, LoRa, as well, as long as there is a software implementation that is capable of working with software-defined radios. We support, we have containers ready to run both srsLT or srsRAN and open interface. And so the actual release that you can run really depends on the softwares that we use. So if tomorrow a new software comes supporting any other features, we can probably port it to Colosseum and run it with Colosseum. Multiple routes. How would you support multiple routes in the same experiment? So this is a very good question. And for instance, for coexistence between Wi-Fi and LTE, and you can ask for Colosseum resources running maybe some of them some cellular software, and some other stacks running a Wi-Fi protocol stack instead. There are quite a few for software-defined radios. And at that point, it's really up to you. You can do like implementation of your custom algorithms or solutions, and you can test them with real radios on a real test bed through these software stacks that are publicly available. And also, we in the same way we have a cellular container for ready to use in Colosseum, we also have some Wi-Fi containers ready to use in Colosseum. So in that case, you just instantiate the cellular container, the Wi-Fi container, and then you can study coexistence effects. Is MIMO supported? So this is really the same answer that Paul gave earlier. So currently, for cellular application in SRS, massive MIMO is not supported, and it will be supported in Colosseum for cellular when the support will be added to the software stacks we're using. In general, Colosseum has a synchronization between the radios. So if you come up with your application that is running MIMO, and you're able to run that application in a different setup, like laboratory setup, chances are that you can run the same application on Colosseum, since all the servers and all the radios are synchronized. Is Colosseum only for functionality validation? It can also be used for performance benchmarking. If so, which performance metrics for 5G SA vRAN can be measured on Colosseum? So I would say Colosseum can both be used for prototyping and designing solutions, but also for benchmarking. And the metrics you can measure are basically for 5G, the KPIs that are available through the software stacks that you use. So for instance, for SRS, you can measure throughput, you can measure resource utilization by the user, you can measure other metrics like this. srsRAN does support 2x2 MIMO. Oh, okay. Yeah, we haven't tested this. But if srsRAN supports that, there are chances that you can use it on Colosseum. And okay, so if there are no other questions, I will move to the next presentation. That is on software framework that we developed here based on srsRAN. Meanwhile, I see another question. Can private companies use Colosseum? The question is yes, but there are arrangements to be done. So please write us. Colosseum is free to use by NSF supported researchers and also DoD researchers. Colosseum is also available to private companies and all other kinds of researchers, but please write us and we can figure out how to give you access. So let me just share my screen with my next presentation. Share screen. Okay. How do I hide this? All right. So today I'm gonna talk to you about Scope. It is a tool that is made available to the research community for designing and prototyping solutions for next-G systems, and with a specific look into the integration between Scope and Colosseum. So basically, with 5G softwareization, we see that there are new trends that involve deploying custom services on general purpose hardware. So you have hardware that is not specialized for a specific function, but the hardware is generic, and you can deploy custom services on demand on this sort of hardware. And you can program the functionalities of this hardware in software. So for instance, you can take a generic Dell or other kind of compute server, and you can instantiate cellular base station or a cellular user on the generic purpose server, and these applications run via software, like the tools we saw earlier and that we will see tomorrow. And you can program the functionalities of your network based on your requirements and the user demand. And the idea of doing this is to dynamically optimize network performance based on maybe high-level intents that are expressed by the network manager or the network operator. But with this, with the possibility of developing new solutions, maybe through also machine learning engines, there is an increasing need for open research tools where researchers and practitioners can prototype these solutions in control environments before they deploy such solutions in the real world, because they want to be sure that their design is flawless and it works in very many different solutions and environments. and conditions. And so we have a need for prototyping tools for the community, and also there's a need for large-scale data sets in case you're using AI or machine learning solutions. You want to be able to test your agents in different conditions and under different network behaviors and traffic demand to be really sure that your solution is capable of adapting to general conditions that you might find to real world deployments, and also that your solution doesn't harm the network in any way, the commercial network. So in the journey toward 5G authorization, we took srsRAN and we extended that with some functionalities. Actually, when we started this, srsRAN wasn't there. We had srsLT, but the concept is similar. And basically, we took srsLT and we extended that with functionalities that weren't there at the time, and such as network slicing functionalities, so the ability of creating virtual slices of the network that are isolated among each other, and where you can run different services with different requirements. We've added some MAC layer functionalities like custom scheduling policies, besides what was already there in SRS, and also some physical layer functionalities like control of modulation and coding schemes of users, or some power control in the transmissions between base stations and the users. On top of this, besides extending srsRAN, we also implemented some automatic tools for data collection of the RAN statistics. And this is very specific to Colosseum, but it can also run on other generic testbeds with minor adjustments. So basically, the idea is that through Colosseum, you can run automatic jobs in batch. So there's some modality of Colosseum that's called batch jobs, and those are automatic jobs that you can pre-configure through some JSON configuration files, and then the jobs can run automatically for you. And the idea is that these jobs, since they're able to automatically run, the missing piece was that we had a need to automatically collecting data from the RAN and to export them to Colosseum after the job was over. So basically, right now you can run the automatic job, collect data automatically, and then after your experiment is done, you can log into the Colosseum system and collect data for offline processing or for training of your machine learning or artificial intelligence solutions. Moreover, we wanted to control the RAN in real time. So we implemented some APIs that are able to talk to SRS, and for instance, tweak the functionalities that pertain to the cellular base station. So for instance, we can adapt the network slicing allocations in real time and the bandwidth allocated to this slicing. We can change the scheduling policies for each of these slices in real time, or modify some physical layer functionalities in real time. So the idea is that you can use this to design your solution that optimizes some performance of the RAN by taking some actions on the RAN configuration and runtime operations. You can hook up your solution with these simple APIs that we will see shortly. And then based on the actual runtime performance of the RAN, you can, for instance, modify these slicing functionalities, the slicing policies, or use a different scaling algorithm to try and improve performance of the network. We offer all of these as an LXC container. So the container has been developed and prototyped and tested on Colosseum, but it has also been ported out of Colosseum to different testbeds and tested and validated on those testbeds as well. And since the implementation is through containers, you can just really take the container from Colosseum and instantiate it on a different testbed that supports LXC and LXD. And you can really start the same experiment, just taking care of maybe minor adjustments to allow the software, the new software, to communicate to the radios and to hook up to the radio interfaces. All of this, in a nutshell, enables the prototyping of custom control logic at a scale, because let's not forget that Colosseum has 256 software-defined radios. So I think there are a few testbeds that have a comparable scale to what Colosseum offers today. So you can really prototype your solution before porting that on real setups and deployments. So just for a comparison, I would say that by using Scope integrated with Colosseum, it's easier to run experiments compared to a traditional lab setup, as without using Scope, so without using just the plain software implementation of the srsRAN network, you can it may take several hours to set up every single machine, like every single computer, and connect it to every single radio that you have, and to manually run every single experiment that you want to perform. On the contrary, with Scope and Colosseum, you can configure your container once. So you reserve a container on Colosseum, and you configure to achieve what you want to achieve. So, for instance, implementing some closed loop control logic, like the ones Michela will show us later on, and you configure your control logic to interact with the cellular software. And you configure that once to do what you want, then you save it, and you can run it multiple times on different servers. So you can essentially the same container on a lot of machines, and you can run it through Colosseum by means of either interactive experiments like what I was showing you earlier, or automatic jobs. And in that case, you just configure the job and the job runs for you. So this is really a lot easier than configuring manually every machine, every radio, and running the experiment manually. On top of this, we also provide a single command line interface as part of our APIs, and that allows you to swiftly modify some of the parameters of the srsRAN base station, and to modify the scenarios you're running on Colosseum, and to easily start the applications without taking care of how things work in detail under the hood, let's say. I mentioned data collection. So another comparison about data collection, if you were to collect data manually on a setup like a laboratory setup without Scope, you would, on top of configuring the machines and running every single experiment that might take several hours, you also need to be pretty sure that your data is consistent. You're collecting data in a real in a good way and in a proper way. So this may take, if you're running, I mean, depending on how long is your campaign to run and how much data you want to collect, may take a really long time to do it this way. On the other hand, running this in Colosseum, once you set up your container once, you can run multiple automatic jobs. These jobs can collect data autonomously. So you log into the Colosseum website, you select, you put in the queue like several jobs that you pre-configured, and these jobs run based on resource availability. But usually they start running in a matter of minutes after you schedule the job. And then these jobs automatically collect data and save them on Colosseum network disks, where you can log into after your experiments are over and just get the data in one shot. So this is generally easier and faster than manually performing a data collection campaign in a laboratory setup. I was talking about Scope and Colosseum, and so let's see in more details. This is one of the scenarios that we developed on Colosseum. This is the Rome downtown scenario, where we have 10 base stations, and these are the blue circles with the number that you see in the picture here. And the base station positions have been taken from an open source database of real world srsRAN deployments, like in this case, the OpenCell ID dataset. And basically what we're doing here is we're emulating the characteristics of the Rome downtown scenario. So we have a set of up to 10 base stations and 40 users, so approximately 10 users for 9 users for each base station. And we deploy softwarized cellular applications and users on Colosseum. After doing this, we can run Colosseum jobs either automatically or manually, and we can evaluate the performance of the network. So in this case, we see that we added also some emulated interference between the nodes. So the base stations, the red and the orange base station are a little bit more stable because they don't have the added emulated interference in their area, while the purple and the light blue base station are closer to the radio that is generating the external interference. So you can see that you are also able to capture all these sorts of effects that you would have in a real world environment. So this is with Colosseum. Instead, if you were to do the same without Colosseum, you will need to go on site with actual radio equipments and computers and whatnot. And basically, you need to run manually your experiments. That is already challenging, but most importantly, the outcome of your experiment might really depend on the hour of the day you're running your experiment and on the weather conditions. Maybe one day it's rainy, or the other day is sunny, or maybe you're running some experiments during the day where there are a lot of people around and there's a lot of traffic, while another experiments run at night might have different outcomes because maybe nobody's around, there's no traffic. So all of this to say that Colosseum allows you to repeat experiments in a reliable way in a controlled environment and keeping the effects of the weather channel that you really want to capture, like the external interference in this example. Just to quickly go through this, since we saw a similar thing in the interactive demonstration. To use Scope on Colosseum, you can just log into the Colosseum website. You ask for a new reservation, and you basically fill a whole bunch of information like name of your reservation, when you would like your resources to be allocated, so date and time, and the duration of your reservation. And then you select the number of nodes and out of the available nodes of Colosseum. And then most importantly, you select the scope image that you want to instantiate on the node. So this is the LXC image that is publicly available to all Colosseum users. And you select the image, and then you can log into your nodes from a terminal session and start experimenting with scope. At a high level, the scope APIs allow you to control some functionalities like network slicing functionalities. And here on the right, there's a high-level example of how scope can be used. Like this is just a toy example to show you how easy it is really to use the scope APIs. So basically, these APIs allow you to control network slicing parameters like associated users to some slices, set the slicing policies, and like the bandwidth allocated to a certain slice, the map algorithm to run on that slice. And you can also, as a plus, modify all of these at runtime. So for an adaptive control of your cellular network. Similarly, you can control multi-layer parameters and functionalities, like you can change the scheduling policies for the network as a whole, or even for just one slice of the network or multiple slices, and you can do this at runtime as well. Or again, you can control physical layer parameters, so like power control and adaptation, or a selection or modulation code scheme for targeted users that your cellular network is serving. And there are also APIs to perform data collection. So in general, data collection is performed automatically, but you can also inquire the data set that has been created at runtime to actually see what is really going on in your network. So maybe you're interested in keeping an eye on the network throughput, and by using these APIs, you can just set the network throughput as a metric that you would like to keep an eye on, and basically you receive statistics, and maybe you figure out something, the throughput for certain slice is going down, maybe the traffic requests are going up, so you allocate more resources to that slice, or you change your scheduling effort. The main idea of releasing scope to the research community is that users can really get the scope container from Colosseum with the custom logic, and they can customize it with their actual controller. So you can hook up controllers and select the scenarios to run on Colosseum, both RF and traffic scenarios. And you can hook up your controller with the scope APIs to optimize network performance at runtime. So you just customize the container, and then you save it and you reload it on Colosseum or in other testbeds, and you run the scope container with your custom logic. And after the experiment is done, you can save metrics for offline parsing and dataset creation. So just to give you a really quick tour about the structure of the scope repo that is in the link in this slide. We have a directory containing the scope APIs, some examples on how to start using scope, and support files for running scope on Colosseum. Then we have some configuration that is used by scope. So for instance, to set the slicing and scheduling of the base station and of the network in general. Then we have the plain SRS GUI. This is just the plain version. And then we have the SRS LT version that we modified with the added scope functionalities for slicing, scheduling, or physical layer parameters that I was mentioning earlier. And then you have the configurations that are used by SRS, like the base station configuration, the user configuration, the core network, so on and so forth. And as for the APIs themselves, we have a scope start script that is used to quickly start scope on Colosseum. So you can see that just by typing this Python line in red here, you can just start the base station in a similar way to what I was doing earlier. And what this script does, it also allows you to parse configuration files that you're feeding to the application, and to start the server application, both base stations and users. And also, as a note, using this quick start script has been tailored to Colosseum specifically. You can still reuse it outside the Colosseum environment, but it might require some minor adjustments for the different testbeds that you use. Then we have a scope API script that contains all the APIs that we use to contact the base station and to reconfigure the base station. And then we have some constants that are used by other scripts and support functions as well. For the example, we have a couple of examples. One example is the heuristic example that is just reading the performance of the run in real time from the dataset that is automatically created by scope, and is just keeping an eye of some metrics like the size of the capacity of the buffer used for the user or the throughput, and is modifying the slicing and scheduling policies in real time based on such metrics. We also have another example script that is slice heuristic script that periodically modifies the slicing allocation of the base station for the various slices, so the PRBs in this case. For the configuration files, and this is really the one of the main files that you can use to configure scope. This is a configuration file where you can specify the various parameters that scope accepts and parses. And we will see about this later on. And then we have a radio config file that is a dummy configuration file that is replaced by Colosseum at runtime while running the batch job. We have another couple of scripts like the heuristic conf file and the slice conf file that are used in the examples I was mentioning earlier. And then we have a bunch of additional support files for Colosseum. About the radio configuration file, so what you can specify in this JSON formatted file, and that is then parsed by scope in real time, is the if you want to capture the packets going on between the radios. So this will be dumped in pickup files. And then you can specify the configuration file. So you give the script a configuration file to parse with all the parameters. We have a parameter that allows you to promptly automatically start hyperv application clients and servers between users and base stations. So you can automatically run a job where the base station will start, and then users will start as well, connect to the base station, and they will run hyperv applications and exchange data. This is very handy if you're using automatic jobs and collecting data offline after the job is over. And then we have some Mac layer configuration, like the scheduling policy. You can set the scheduling policy for the whole network. So for every user of the network, you can set a scheduling policy among the round robin, water filling, and proportionally fair scheduling policies. And then you have the option to force the downlink modulation or uplink modulation for certain users you might want to do so. And then we have a bunch of network slicing functionalities, like if you want to associate users to a certain slice. And if you want to use network slicing at all, or maybe you just don't want to use network slicing, so you can disable this functionality. The allocation of these slicing policies between the various slices and the configuration of certain slice, like scheduling policies, bandwidth of the slice, resources allocated to the slice, so on and so forth. The scheduling policy of the slice. And then we have another file that allows you to basically run the various functionalities of the scope framework, or disable them if you want to compare them with a baseline cellular implementation, for instance. And then there is a config directory that gets populated at a runtime with the user-related parameters, and also a metrics directory that saves all of your runtime metrics from the run in a nice and clean way for you to either parse it at runtime or to parse it offline. So the metrics are logged in this directory at runtime. We also have a bunch of configuration files for the slicing. So there's a slicing directory that contains all the information that Scope uses for configuring slicing and setting up slicing, such as allows you to specify slicing and allocation parameters for the different tenants of your cellular networks, or again to modify the scheduling policy for certain slices, or again to associate certain users on to certain slices of the network. So we might have some slices serving enhanced mobile broadband applications, and other slices that are serving low latency applications instead. We can specify through other configuration files, like the modulation, if you want to force any modulation of the users, both in downlink and uplink. And this is mostly for the configuration files. And talking about the scenarios, we designed some cellular scenarios like the one I was showing you earlier. And these scenarios allow you to specify various effects to capture in Colosseum. Like you can have scenarios that have certain path loss, certain distribution between the users on the base station, and specify the mobility and the speed of the users. I can also similarly modify, specify the traffic flows and type of traffic between the nodes. And as an example of scenarios that we created, there are the Rome scenario, the Boston scenario, and the Salt Lake City scenario, like the one we were showing earlier. And these are all scenarios ready to use in Colosseum. So the idea with Scope is that Scope can be used on Colosseum and ported to different aspects. So first, you prototype your solution on Colosseum, and you test it in a control environment on this network emulator. And then when you're happy with your solution, you can validate the same solution in a real environment by just moving your LXC container from Colosseum to the to the an actual external testbed. And after doing that, you can also test the capabilities of your solutions on large-scale testbeds like the city-scale platform or platforms of the Power program. We did that. We tested, we prototyped a certain solution first on Colosseum and then on the Arena testbed. This is the testbed we have here at this university, and then on the public platform. And we can see that even if the raw numbers are not exactly the same because of the different conditions of the testbed, because one is the channel emulator, the other are real-world testbeds, the performance that we got are consistent across different testbeds. And this is it for this part of the presentation. And if you have any questions, yeah, I see we have some questions in the chat here. So we have so is it possible to interconnect Colosseum with other platforms like Powder and AirPow? So thank you for this question. So yeah, you can surely test a solution on Colosseum first, like, and then you get your LXC container and you port it to different testbed, like Powder, for instance. I'm assuming AirPow has similar capabilities, but AirPow literally opened this week, if I'm not wrong. So we haven't tested it so far, but on Powder, it is definitely possible to do so. Okay, we have a question on FPGA images. Does system allow the user FNOC? Yes, you can just yeah, you can just flash the FPGA image through JTAG and customize the FPGA image of the X10 in any way you want. We have some containers with Vivado Lab installed that allow you to do so. No, scope is not really an acronym, was like some name we ended up with. I believe we in the paper describing scope, we ended up with an acronym like Softwarize Cellular Open Prototyping Environment, but it's just all started from the acronym, and then we look for a name to associate to the acronym. And how does scope checks the scope config? So the configuration files are reloaded periodically, and you can specify the periodicity of this operation at runtime. So periodically, the framework, as of now, checks the configuration files and modifies the configuration of the network if it's changed since the last check. Can we change slice user association at runtime? Yeah, this is possible. You can change the slice user association at runtime by using scope. Is scope ORAN compatible? It actually is. Thank you for this question, and I believe Michele will talk about this in the next presentation. So just the quick answer is yes, and then I believe Michele will tell you more about this later on. Yeah, feel free to reach out if you have additional questions, and I will do my best to answer them offline. Thank you so much.
All right, thanks, Leonardo, for the demo and the presentation. I hope we gave you an idea of how you can use Colosseum to do this kind of cellular and wireless research. And